Everybody to the Dana-Farber Cancer Institute Data Science Zoominar. Today, we are super excited to have David Spiegelhalter with us. David was the chair of the Winton Centre for Risk and Evidence Communication, which is dedicated to improving the way that quantitative evidence is used in society. He has been an applied statistician for over 3 decades, and has been involved in several projects with important implications. He is a statistician in the public eye, definitely, and we'll be talking about that. His academic work is focused on Bayesian statistics, including being the co-developer of BUGS and winBUGS, a piece of software a lot of us have used, and also biomedical applications and science communication. He won numerous awards for his work, including being knighted in 2014, and he is the author of the very popular book, The Art of Statistics, which I highly recommend. You will read it in between 2 and 3 days. It's very interesting, hard to put down. And even for statisticians that already know most of the statistics in it, it's a great read because it can help you explain it and maybe think about it in slightly different ways. So thanks, David, for joining us.
Great pleasure to be here.
Thank you. So I'll go ahead and start right away with my first question. So I think that we're at a crucial point right now in science with data at the center. We've seen it amplified during the COVID pandemic, and statistics has greatly matured as a field during the 20th century to the point that it's used in most scientific disciplines. But recently, when I say recently, I guess I mean last 10, 20 years, we've seen a shift to data-driven research that makes statistics even more central to science. However, statistics education, at least in my opinion, has lagged a bit behind. And as a result, you have what I think is a worrisome increase in the number of scientists using statistics, interpreting data without really understanding statistics. And I think your efforts to improve understanding of statistics and the way we communicate uncertainty in particular are key to the continued success of the scientific enterprise. So my question, after giving you that opinion, is what do you think the future holds? Or if you disagree with some of what I said, please let us know.
Okay, no, I basically agree with what you said. Is that, I've been in statistics for a long time, and back when I started, it had a fairly low profile, and people tended to be rather obsessed with the philosophy and so on. And you couldn't actually do that much anyway. You had these big programs like SPSS and BMDP, and then S came along, and then R, and then modern computing and Monte Carlo methods and so on. And suddenly, we could do so much. And it's been a very exciting time. It's been a great time to be in statistics, to watch it develop. And I think the rise of data science is just wonderful. It is very good because I regard data science as something which is bigger than statistics. Ideas of statistical inference overlap in the Venn diagram. Obviously, they're terribly important, but data science is so much bigger in terms of what its ambitions are and what it can be applied to. So I think this is all very, very exciting. I wrote the book. I was going to call it Statistics for Data Science, because the whole point of it, I think, was to bring the important and challenging ideas of statistical inference to an audience that may be quite adept at doing the computation and doing things with data. But I always just quote Nate Silver's quote from The Signal and the Noise, where he says the data does not speak for itself. We imbue it with meaning. I start my book with that quote from Nate. And I believe that very strongly, that just because we've got masses of data, it doesn't just offer up its secrets like some magic potion that reveals itself, like some oracle. We've got to be very careful about the claims we make on the basis of the data. And that's what statistical inference is about, I think. Reliable, trustworthy claims arising from data. And of course, this COVID business has brought this home, so strongly. The claims that are made backwards and forwards, everyone's saying what they think, and they're always saying they've got evidence for it, and there's always statistics. They're always quoting to back it up. So it's a complete, battleground out there using statistics, which I think is great, is wonderful. I mean, in a way, it is particularly challenging because it means the public is suddenly being exposed to the uncertainties of the science, the disputes in the science and numbers, the unreliability of so much data. And so any illusion that, which was wrong, they had, that somehow data were facts about the world, true facts, and that science was a collection of fixed knowledge, you know, I hope has got out the window, because that's actually wrong. But it does mean that you know, there is this challenge to our professions to deal with that in an open and honest way. Okay, yeah, education. I've been very influenced by Andrew Gelman, his approach to statistics education. I've been very influenced by the New Zealand people, you know, who New Zealand is essentially the World Centre for Statistics Education, and not just because of the R, you know, relationship. They've been working both in schools and at universities, especially Auckland, to develop a real philosophy of statistics education. And when I've been to ASA meetings, I always go to the educational ones to see the arguments that are going on. And I've been hugely influenced. And if you look at the book, you'll notice the effect of this influence. First of all, probability theory doesn't appear until 2/3 of the way through. Statistical inference, in terms of, you know, the formula that give rise to confidence interval, you know, 3/4 of the way through. And because the issues, the important issues about statistics and what you can learn from data, are much bigger than just this business of, you know, the tests we do and the estimates we do and this sort of stuff. They're far more concerned with the quality of the data, the biases in it. What can we actually answer our questions with the data? Can we conclude causation, no matter how fancy an analysis we do? What sort of designs might we choose when we can actually experiment, and so on? And all these have got almost nothing to do with statistical inference. And what I found is that, and this was again stolen from New Zealand, I think, is that you can get through all the ideas of sampling, of sample and population and generalization, just with the idea of picking at random. That's all you need. You don't need probability theory. You just need the idea of picking at random. And every kid knows about picking at random. And so you can get so far from that. And so therefore I introduced bootstrapping before the formulas for confidence intervals. Not that I give the formulas for confidence intervals.
That seems to be a common theme that I see. In my online book, we do the same. We do Monte Carlo before we even introduce any probability formulas.
Yeah,
and
absolutely.
with a computer, being able to run it on the computer, like the student can actually see it happen in front of them.
And then for me, what I argue is that the mathematical approach that we all learned and which I taught is just a neat way of not having to do these enormous computer runs.
Exactly.
It's a shortcut. Wow, we can just use a formula and get the answer. But it's the mathematics should not drive the conclusions. It should be just seen as a useful tool at the end. And it took me ages. I've got to spend ages rearranging chapters, all this kind of stuff. One of the problems with that is Bayesian methods. Now, I've been, you know, my whole career has been in Bayesian methods. You know, I was indoctrinated into it really when I was 18, I think. Yeah, and I'm, you know, ideologically, well, we might as well get on to this. I'm a convinced subjectivist Bayesian, you know, and that's where I was brought up, and I still believe that, although I use all sorts of methods the whole time. If you scratch me and ask me what probability is, I'll take a completely subjectivist line on that. It doesn't exist, for example. So but Bayesian methods do require probability theory. After all, you know, it's a theorem of probability. And so sadly, I found is that Bayesian, the methods had to be left until a lot later, until nearly the end of the book, which I think is unfortunate. Although we can still bring in the ideas that probability is about judgment, it's about assessment, it's not a property of the outside world, you know, much earlier on, which I do.
Yeah, it is easier to do a frequentist simulation than a Bayesian one. But it still can be done. But I see what you're saying, that it's yeah. So on a related topic, this is in a way a concern that it's a concern I have now after teaching data science for I don't know how many years now, that I do take that approach that we start without formulas. And then we have all these students that are very happy about it because all of a sudden they like the statistics class, right? And they can actually do stuff.
Yeah.
But that happiness ends when we start talking about probability and inference for many of them.
The sample, as soon as you get to the sample distribution of the sample mean, that's it. So,
but then I worry that we're, because we like happy students, that we're skipping. I mean, not everybody, but, and clearly not you in your book, but that there's this tendency to teach data science courses without probability and inference, which I think is a huge mistake. I don't know.
Yep,
but
I would agree. I think it needs to be in there, because otherwise you've not really got a set of principles from which to act. You know, maybe they're idealized principles and probability models, which of course don't exist and are all wrong, but are incredibly useful. The ideas of statistical inference as it is carried out very usefully throughout the whole of science, you know, I think that is an integral part of data science. Maybe not for everybody. I think you could actually, you know, you could do a lot in, you can get, as I say, you can get a huge long way. You can even build, you know, predictive algorithms and so on. You don't need probability theory for that. Until, as I show as I mentioned, because I do that in the book before probability theory, except of course a decent algorithm will produce a probability. And then you've got the idea of how do you assess how good those probabilities are, and which I think is absolutely vital. The assessment of the trustworthiness of the probabilities that come out of an algorithm, no matter how it was generated, whether it's a logistic regression or a random forest or whatever it was. You know, when it gives a probability, you want to know whether you can believe it or not. And I think this is a much more core issue than, in a way, a lot of statistical inferences. So I would be a bit torn. I think that in data science, there's a huge amount you can do before you bring in probability and statistical inference, but it is a very important part. But you must recognize that it's not all students are going to warm to it, perhaps.
Right. Right. And if you want to be the main analyst in any kind of project, well, I mean, I guess there's an exception where summary statistics is enough, but in most analyses, you will need to understand it and also know some of what already exists, so you're not reinventing the wheel.
Yeah.
Absolutely. So now related to that same idea is something that I saw in your book. You actually say it explicitly. There's a difference between data science and data literacy. And I guess when we teach that I think is an important thing we need to accept, is that some students, I mean, given the world we live in, everybody needs data literacy, I think, pretty much. But data science is something else, and it doesn't mean we can't teach students how to understand a paper or a news article that talks about statistics without being able to reproduce the analysis themselves, for example. But do you have an experience in teaching this or dealing with your university?
I mean, not explicit courses in data literacy, because as you say, data literacy is something to do with the whole of society, both whether you're a citizen or whether you're a professional or whatever. I mean, just broadly, I would say data science is the act of actually doing the work and producing things, and data literacy can include that, but actually is much more concerned as a consumer, as the audience, to claims based on data, to which we all are. And again, this COVID crisis, we have been, you know, an audience to countless claims, and let alone your elections. I mean, so, you know, there's endless stuff for which we are the audience, and we need to be able to exercise some judicial, you know, critique, or, you know, some sort of skepticism or argument about it. We need to be able to critique what the claims are being made. And so I believe this is, you know, many people have said this is an essential skill for modern citizenry and modern professions across the whole board, is data literacy. And that means the ability to take apart and ask the right questions when someone's making a claim based on data, and not just be baffled by it because, oh, they said, oh, we used a machine learning algorithm, or we use this, we've got this, and a whole lot of jargon and big numbers and this sort of nonsense. So, you need to be able to say, no, hang on, I want some trustworthy communication of these numbers. Tell me what's really going on. I need to be able to understand that. Not everybody. Some people might just have to take it on trust. But I think this is terribly important. I mean, it's difficult. You could say, in the way I work in that area, not just me, but many people, the whole time, and nearly all my communication during the COVID thing has been educational in some process. It's not been arguing for lockdown or anti-lockdown or for masks or anti-mask. None of that. I won't touch any of that stuff. I've got no agenda. I'm not on anybody's side. I'm not going to tell anyone what to do or even advise them what to do and what should be done. That's not my job. My job is to try to clarify the arguments. And if someone's making a really stupid argument, to point it out, with as tough as you can make it. So I really go in with hard on somebody who's manipulating the argument through misuse of data or misuse of statistics. So, but I'm not. It doesn't mean I'm on one side or another. Just anybody who misuses the data, I feel I can critique. Can I just show you one thing? Can I show you the kind of thing I've been doing during this COVID crisis?
Absolutely.
I just want to. Let me just see if I can make this work. I might be able to make this work. Okay, so what I'm going to do is just to show you a brief. I'm going to try to share my screen, and I'm going to show you a brief little clip from an interview I did in the main politics program in the UK. It was a Sunday morning, the Andrew Marr show. This was back in May, and this is about we were getting then daily briefings from the Prime Minister and others in which there were a lot of statistics being quoted. Okay. So this is what I said: share computer sound, optimize screen share. Okay. And tell me if you can't hear it.
They're now very familiar with these daily press briefings. How well are they working, do you think?
Well, I watched yesterday's, and frankly, I found it completely embarrassing. We get told lots of big numbers, imprecise numbers of tests being done, 96,878. Well, that's not how many were done yesterday. That includes people that were posted out, tests that were posted out. We're told 31,587 people have died. No, they haven't. It's far more than that. So I think this is, actually not trustworthy communication of statistics. And it's such a missed opportunity. There's the public out there who are broadly very supportive of the measures. They're hungry for details, for facts, for genuine information, and yet they get fed this, what I call number theatre, which seems to be coordinated really much more by a number 10 communications team rather than genuinely trying to inform people about what's going on. I just wish that the data was being brought together and presented by people who really knew its strengths and limitations and could treat the audience with some respect.
Okay, so that
very good.
Yeah, that was my kind of diatribe. And let me see if I can get rid of that. And what am I doing? Stop sharing. Okay. Yeah. So that was my kind of diatribe I got a chance to do, which went a bit viral and got mentioned all over the place. So I don't do that kind of attack often. But it was just showed, I think, how intensely irritated statisticians were getting by the way in which numbers were just being pulled out of a hat and waved about. Here's a big number, here's another big number.
And then there's the dashboards with the red thing.
Yeah. And some terrible, awful graphs that nobody could read and you didn't know what they meant. No, really dreadful stuff. So, and it has got better a bit better.
Yeah, I like the point about the number theater, in particular when they're putting out these numbers that are very precise, right?
Yeah.
72,158.
Oh God, yeah. But as soon as someone starts quoting numbers to 6 significant figures, you just shouldn't take any notice of them.
And that is one. There's one that I continue to see as a problem is that because the measured cases, the detected cases are reported as if that's the number of people that have COVID, right? It's like they're not taking into account all the ones that aren't being measured. I mean, I don't know about in the US, UK, the media has finally realized that. And also
they report them every day, but that's the number that have been reported on that day. Actually, they happened, maybe ages ago. Sometimes some of the deaths happened ages ago. So, and so still the media will sometimes say, 574 deaths happened yesterday, or so, which is just, just completely wrong. So, it is a problem that, in a way, so many more journalists have been dealing with numbers more than would normally deal with numbers, and who are not very data literate. They're just not data literate. However, some of them have really got good. There's always the problem with diagnostic tests, false positive rates and predictive value. When you get a positive, what proportion of positive tests are actually false positive? Terribly misleading stuff. Very badly explained on the whole. But some journalists have really got quite good at it. And
I had that experience with Nicholas Kristof from New York Times. Asked me to help him with something, and I was very impressed by how quickly he understood statistical concepts, and also how open he was for when I told him that what he wanted to say was which was a little bit sensationalist, was not quite right. He immediately stopped it. Like he was very open to that once you explained to them why it wasn't quite right.
It's been a great time to be a statistician dealing with the media, because it's, in a way, it's a seller's market. They need you so much. They can't afford to upset you too much, because they so want, independent, some fairly independent input and critique and commentary. And so they're actually extremely generous. So, I mean, I know it's more familiar in the US, I think, but in UK, journalists almost never give you back your quotes, allow you to check the quotes. They never tell you what they're going to use. But it's now journalists, they do it. Partly I just demand it now. I won't just have a conversation with a journalist. So I'm not going to do it. I'll give you some quotes, or if I have a conversation, you've got to tell me what quotes you're using. And I in a way, we can make demands now in a way that we never could. I've had newspaper headlines changed. I've had newspaper, because I just complain, just phone up and complain and shout and scream, and it works.
Yeah. So that leads me to one of my questions that I wanted to ask you, related to the press and how to communicate uncertainty. And it's this experience I had with estimating excess deaths in Puerto Rico after Hurricane Maria. I experienced much of what you described. There was a press release which I edited very aggressively to make it clear that there was uncertainty in our measure. I did use confidence intervals, and I think you're going to tell me that was a mistake, and I think I might agree with that. But I was like, every number, take out all the numbers and instead put in a confidence interval. That was what I was trying to go for, so that the uncertainty was very in your face. It was a very imprecise number because we used a survey, and it wasn't what the paper wasn't just about that, but that was like the press just went crazy over that, and they took the number, the middle of the confidence interval, and went with it. Sorry,
did you give the estimate, or did they take the middle of the range?
No, we did give it. We did give it. No. Yeah, no, that's right. So the other thing we did that was that now I realize maybe it was a mistake, was we put the number, the estimate, we rounded it to the nearest integer, right? So it was 4645, which now you'll see, like if you go to Puerto Rico, that number is graffitied around the walls of some parts of the island. Yeah. Right. So then when you give that number, the precision wasn't enough to really give that. So maybe we should have said 4,000, or we should have said more than 800. Yeah. But do you have a rule of thumb for how to do that? How to report?
Yeah. Okay.
Imprecise estimates like this?
Yeah, it's very, very tricky. The first thing is, I work with a team of psychologists now. We've been doing quite a lot of research in which we look at how giving a range for a number influences people's trust in the source. And if you can give a range, there's no decrease in trust in the source. So the first thing is, you've got to be unapologetic about expressing uncertainty. Mm-hmm. Now, the issue there is about which range do you give? Do you have to give 95%, or could you give interquartile, something a bit narrower? Which again, I think is quite reasonable, because sometimes these things, look so wide, it's like you're not giving any information at all. Because you should really communicate that you give a range. The problem is that, and people have done some research on that, is that many people might interpret it, oh, it's equally likely to be anywhere in the range, which it isn't.
And they might even take the higher one.
Yeah. It could
as
be
many as.
As many as. Oh, no, but there's a trick to defeat that. People were doing that on climate change. When they give a range of future temperatures, people were saying, oh, it could be as high as 12 degrees and change. And I was in a group that changed the wording of the communication. And so what we communicated is it's very unlikely to be greater than 12 degrees. Same number, just the top end of the interval, but it changes it's changing it from a negative to a positive frame. And so that does not attract the same kind of, obsessive attention. So purely the wording about what the top end of an interval does can change its impact in its communication. We have to be aware of those kinds of things, about just the framing of the numbers can make a massive difference. So basically, I think a range, ideally, you don't give the point estimate. When the Bank of England give its forecasts for inflation, things like that, they don't give a point estimate. They just do a fan chart, and they give a 30%, 60%, and 90% interval, which I really like in different shades. So the eye is drawn to the center, to the middle, but not to a point. If you do it visually, I think it's a very effective way to do it. Yeah.
Well, we had the plots that those are definitely there with a big, the dot.
Yeah,
and
the big thing. But as soon as you get the central number, that's all they will use.
And then how about significant digits?
Oh, you shouldn't have done that.
But what is do you have a rule of thumb about how many to include given if you know your standard error?
Only depends on the width of the interval.
Yeah.
So if the interval takes you from 4,900 to 4,200 or something like that, you should certainly only give it to two figures. So you should give it to the precision that the interval allows you to give. So the number of significant figures is governed by the width of the interval. So you should just use very few significant figures. And that encourages a feeling of uncertainty, because if you just said 4,000, nobody believes there are actually 4,000. And so it actually works rather well. I mean, the other thing is just to say around 4,000, because that's actually all or around 4,500. That's all you can say. And so I think, that's actually being honest and communicates to any reader, well, there's a lot of uncertainty there.
Yeah, no, that's definitely lesson learned.
The other message I always say is that for all this stuff, there's no correct way to do any of this, is to test it. If you've got an important message out, test it on audiences to see what they're getting from it. Even if it's just your colleagues, your friends, your family, test it out. Because we find it very difficult to judge these things.
Mm-hmm. Yeah, good point. Testing it out. I do that now with my daughters in particular.
Yeah, exactly. Ask your kids.
You understand what this means?
Yeah. No, ask your kids is the best way to do it.
That's good advice. But you know what? That's like, what class do we learn this in a PhD in statistics? That's not. Maybe we should have a 2-week workshop for everybody. How to talk to the.
Communication is an integral part of what you might call the data cycle, which I build a whole book around, which is, which starts with a problem, then it goes on to just seeing if there is any data that could help you answer the problem, and then there's collecting and designing the sound, cleaning the data, getting it, and then there's the analysis, just one little bit, and then there's the conclusions and the communication. So I think every statistician and data scientist should have communication skills, and that includes not only in terms of visualizations, which is accepted as, of course, is a very important part of data science and statistics, not just visualizations, but also verbal explanations. We're in the Royal Statistical Society now, we've got ambassadors, and we give them media training. And I help with some of that. And it's wonderful. We just say, well, okay, explain a confidence interval or whatever like that, or explain what this interval means. And then they start saying, oh, this is a confidence interval. So you can't use the term confidence interval. Sorry, you can't use it. You're not allowed to. Come on, without that. And I want it in the length of a tweet. So they're allowed a paragraph, and then they have to do it in the length of a tweet. So it's a real challenge that you get to explain things, and so it means you can never do it so it's absolutely right. It's just got to be not wrong. And we mustn't be too pedantic about it. Yeah.
And you're saying, yeah, the pedantic thing, like the confidence interval is very rare for a non-statistician to get right.
Well, don't
The
bother.
definition.
Nobody cares. Nobody cares.
So then some statisticians get really angry at you.
Oh, I do. Oh, I do. Among statisticians, I get obsessively angry with if people get it wrong and don't distinguish between a Bayesian and a confidence interval. I'm obsessively angry with it. But if you're talking to the general public, it's a complete waste of time to go into it. What I'm interested in,
but you say we shouldn't even use the term. Just like,
no, I wouldn't. I'd never use the term confidence interval. I mean, what's interesting, almost all the COVID modeling going on is Bayesian now, so these are all credible intervals, and so I would just use margin of error, range, or possibly uncertainty interval.
Yeah.
So one of those. You don't have to call it a confidence interval. Who cares? Nobody. But can I show you something else? What do you think about this? Because as I said, uncertainty communication is so important. So we always emphasize, part of demonstrating trustworthiness is, is admitting uncertainty about what you know. So you can give a range about a number, which I think is very valuable, doesn't decrease trust. But you can also acknowledge the fact that the evidence isn't very good. And this is something that I think is incredibly important that we should get better at just admitting that our models aren't very good. So this is an example. I don't know what you think about this. So in the UK at the moment, the R number, which is the average number of people that each person with COVID infects, there's 8 different modeling groups in the UK, all trying to estimate R. So all trying to estimate the average, all trying to estimate the same quantity from essentially the same data. They've got multiple data sources. And this recently was the 8 different estimates from the different groups with their intervals. They're all doing Bayesian modeling, so these are credible intervals. And look at them. They're all over the place. Well, they all broadly say, it's not that high, it's roughly between 1 and 2 somewhere. But look at the precision of some of those estimates, and they don't even overlap. Now, this is the same quantity being estimated from the same data, and yet the intervals don't even overlap. Think how disastrous it would be if the government was just looking at one of these groups. Now, actually, seeing them like that, then they all get together in a room and they decide, well, we're going to say that, and that's going to be announced to the public, and that's what they get to. I don't know what you feel about this, but the point is that this is precision, but not accuracy. They can't all be right. They don't even overlap. Because they're all the uncertainty estimates in the classic Bayesian way, unfortunately. Bayesian estimates are conditional on the truth of the model. They come out of the probability model.
Right, so there's a variability here that is not described in the interval, having to do with how people choose the model, and that's really hard to
the between model and the model and basic uncertainty or doubt about the model, the systematic biases coming in from the model are not being reflected in those intervals. So those intervals are deeply unreliable. And that's what's happening, and that's what you get if you just feed something through a model. So thank goodness there's eight teams doing it.
This reminds me of that famous enduring values paper where they have the speed of light estimates.
Oh yes, no, exactly. And when I've talked about this before, someone has mentioned about metrology, and I'm a big fan. Statisticians and data don't know about metrology enough, which is like the speed of light. You're trying to measure things, and in that whole area, they've seen this for years, a century. They've known this, that essentially within experiment estimates of precision are far too tight. Don't reflect the real uncertainties. And so they got type A and type B uncertainty. This is type A uncertainty. Type B uncertainty is to do with the systematic biases because of the measurement process. And they are happy for those to be assessed subjectively as a matter of judgment.
But here the uncertainty comes from the statisticians, the way they work. It's not the measurement, right?
Well, no, but it's the model. Yeah, it's the fact they all choose different structures for their models. Some of them using complicated ones, some using simple ones. Of course, the more simple ones will tend to lead to the tighter intervals. So it's deeply disillusioned. So
it's interesting that when I see that plot, I think that's not that bad. given what I've seen in my life.
But as I pointed out, thank goodness there's 8 of them doing it. That we see them all. I mean, wouldn't that be awful if we just saw one of those?
That plot is so much more informative than a single one.
Exactly. So it's really not a bad thing, but it does show all models are wrong and some are useful. And that's why I do think that any team communicating those should also say their reliability in the evidence. So I'd just like to show some people who are doing that. In the UK, we've got these what works centres that evaluate the evidence for different policies. Incredibly important. They're brilliant. And they've got one for education, for example, and they produce a toolkit where they list all these different things you can do in the classroom. And it's like TripAdvisor. They give them star ratings depending on, so here, aspiration intervention. So that's quite expensive. This is the estimate of how many months of educational gain there is. So it doesn't seem to work. And this is a measure of how good the evidence is. In other words, it's rubbish evidence anyway. But down here, collaborative learning is fairly cheap, seems to work, and there's good evidence. So I think rather than some completely spurious confidence interval, I think this is very powerful. And what we found, we've got our SAGE as our.
And I'm sorry, can I? What are I missed? How are those little locks?
Yeah, well,
it's a committee that does it.
Yeah, it's a kind of but they'll have some guidelines as how to assess the strength of the evidence. It's very in medicine. There's a grade system, which is a star rating just with 4 levels. And there's a kind of algorithm. If you're a randomized trial, you start off at 3, and then you might go up for some things and down for another. So, every area has got its own kind of rules of thumb for deciding those. But you can drill down and find out where it came from. I think this is really powerful. And
I love it. I love it. I've always had this idea that, I've had an idea that, never implemented it because it seems hard to do, which you form a committee that takes the papers in biomedicine that seem to get the most attention, because we don't have time to read them all. But at least take the ones that are getting attention and give them some kind of grade like that.
Give them a star rating. Yeah.
Because some of them are obviously wrong to statisticians. Like I mean, the most famous ones are like this Potty-Nevins scandal from Duke. That was all the statisticians knew the paper was wrong, but the editors and other referees took a little bit longer to catch up.
Yeah, but I mean, the trouble is you might get sued. So I'd be careful. I'd be careful with that idea. but SAGE is the committee of scientists that give the advice to the government, and they're doing this at the moment. So when they're reviewing the evidence for wearing face coverings outdoors, they said very low impact, and they got high confidence. There's no point in wearing face masks outdoors, they claim. Whereas closure of places of worship and community centres reduce our the interval is up to between 0 and 0.1, but they're not even really confident about that interval. And some of the stuff they do, they just say they've got low confidence of what these impacts are. So I think this is a really powerful idea and something I'm kind of trying to promote in any evidence communication, that just giving an interval is not enough because I don't believe the interval.
Yeah, no, but it's tricky, right? Because you're going to be seen as wishy-washy. That's the danger.
Well, yeah, but that's the point. I think that, I think that, again, our research shows that if we call it unapologetic uncertainty. If you just say, we know a lot, this is what we know, but we don't know this, and just be honest, then there's no reduction in trust in the source. So we're really encouraging people to get up there, get up there and proclaim their uncertainty. Boldly.
I'll take that advice. So I'm sorry, I've been neglecting the audience. So let me ask at least one of the questions. Do you have any advice for statisticians for whom the growth of data science has meant more and more colleagues with poor understanding of probability and mathematics? This is from Dan Hapty.
Yeah, okay. Well, I mean, that's why I wrote the book. Although I wasn't doing the mathematics in any great detail, it was to try to point out to people doing data science that there is this world of statistical inference, probability-based statistical inference, which sort of, has been quite useful for 100 and something, 150 years or so. So don't ignore it. It's all there. It's very useful. Don't ignore it. Don't think that the data is going to just give up its secrets. So I do think, I'm not sure about advice. I think I think demonstrate by your work that a knowledge of probability modeling and statistical inference and evidence-based conclusions, etc., are valuable. I think you have to demonstrate. I think you've got to prove it all over again that this is a valuable addition to those wonderful data skills that so many people have got now, and that, general ideas, and in particular when in so many areas, particular when it is data science being used in science, because then the reliability of your claims is absolutely essential. You can't just come up with something that works quite well. I mean, if you're doing a recommendation system or something like that, then obviously you've got something you're trying to match, you're trying to optimize, and so on, and you try lots of stuff, and you find the one that works, and that's fine. It's a purely empirical bit of work. But if you're trying to do something where you're actually trying to discover something about the truth about the world, then that's not enough. You have to be able to say, you have to be able to state your conclusion and your confidence in that conclusion, and the confidence must be reliable. It's this sort of second order property that statistics is so interested in, that it not only wants to make an estimate or a claim, it wants to be able to say how confident you are in that claim. And for that, and what we've just been talking about is that confidence itself should be a reliable statement.
Yeah.
But you have to demonstrate it. I think you've got to earn it. You got to earn it.
You got to earn it. Right? That's what I was going to say, that it takes time to earn it. It doesn't just happen because you have a degree or just because you make a statement.
I mean, the other thing is that, and I suppose we're coming back to the original thing, is that you do have to revise statistics teaching. If you're going to try to get, data, people are coming up from, a lot of people coming into data science from all sorts of areas, which is great. It's wonderful. But if you then say, oh, now we're going to do statistics, and you immediately plow into the sample distribution, the sample mean, well, God's sakes, really, who's going to want to endure that? So I think that you do need to think very carefully about how that education is done.
Great. Well, we're almost out of time, so I'll let you give final thoughts for them with those, to add to that to our audience before we go. Any final thoughts for our data science audience? Oh,
I don't know. I think it's such a fantastic profession to be in. I mean, it is really an exciting time. But I think that what you have to really watch out for is trustworthy claims. Because you may be able to do something quite fancy and clever and things like that. It's just like, if you've got a visualization, you really got to check whether it's telling the appropriate story and isn't just looking good. I mean, I've seen a lot of visualizations that I think, at first it looks pretty, and I think, actually, really, what's the point of this? It's just doing it for the sake of it. So no, I think trustworthy communication, and to I think that's basically my running theme, and that probability and statistics are valuable things, but it's not all there is at all.
All right. Well, thanks, David, for joining us. Here's a book. I highly recommend it.
Yeah, so do I. Should be out in paperback next year as well. So with some of the typos corrected.
Okay, great. Well, thanks again, David, and it was great having you.
Not at all. Great pleasure. Thank you very much.
I hope to talk to you soon in the future.
Yeah. Okay. Great.
Bye, everybody.
Bye. Bye.